Shalom lekulam. Hello to all. We want to just start our webinar. Thank you all for a great feedback from our last few sessions. So you're encouraging us to continue the webinar and continue to share with you our knowledge. In today's session, I will just let Chris to start. For any question you have, please use the Q&A bar in the bottom. Part of that we will answer online. Part of that I will ask Chris in the end of his lecture. So again, thank you for joining us, especially in such crazy days of supply chain and all the logistic issue. I think it's important to go back to the basic, to the technical issues and to things you need to know and we want to share with you. So Chris, thank you very much to making that session, and you can start.
Thanks very much. Thanks very much, Jared. Okay, first of all, a very warm welcome from the UK where I'm sitting. It'd be nice to be with you in person. But unfortunately, as Yarov said, this is a time where we have all these COVID issues at the moment. Okay, I'm just going to share my screen. Just bear with me. Okay, so hopefully you can now see my header screen. As the title states, this is the session is the secrets behind the power supply specifications. So it's a little bit of fun, but there's some serious parameters behind this. So just as an introduction to myself, I'm Chris Maidment. I'm the technical marketing manager for TDK-Lambda. My responsibilities is the market and application analysis for power supplies, and also the product strategy. So I cover the EMEA region, which luckily for me also covers Israel. So I'm very happy about this. My experience is a lot of power. So I trained on UPS systems. And then for the last 26 years, I've been working under Siemens, EPCOS and TDK in electronic components, and particularly the electrolytic capacitors, which are critical for the power supply's performance and lifetime. And for the last year, I've been with TDK-Lambda, so I'm enjoying myself here. My application knowledge is primarily power and also high frequency magnetics as well. And if you have any questions outside of this forum, then please feel free to link in with me or send me a message on LinkedIn. That's absolutely fine. Okay, I'm just going to quickly go through these slides. So the objective today is really to give you an insight into the not so well known facts about the AC/DC parameters. I also want to add some application hints and tips as well. So the plan is I'll be using, as an example, the CUS400M. It's a 400 watt power supply. Why am I using this particular power supply? It has multiple uses. So it's a medical grade power supply. It's also used in industrial applications. There's options for convection, conduction, and forced cooling, as well as auxiliary supplies and a peak power rating. So it's quite an interesting power supply from that perspective. As we will be revealing some datasheet secrets, then it is really appropriate that we have a top secret gadget that this power supply will be supporting. So in this case, the CUS400M will be powering a long-range optical and audio detector, or we call it LOAD for short. Just so you can see what we're dealing with. So this is the CUS400M. So there we go. So this is actually in the U channel. So that's the power supply we're going to be looking at today. Oh, one too far. Okay, so there we go. So the resources that I've been using to pull this presentation are totally available to you. They're available on our website. So I'm taking information from a datasheet, the installation manual, the application notes, and also the reliability and emissions data. So you can find this publicly on the TDK-Lambda website. In addition, there's some technical resources there, and this is glossary of terms, and also the TDK-Lambda blog. So it's well worth having a search through those. So we're particularly looking at data sheets today. So the question that always first came into my mind is, why do manufacturers do not include all technical information in the data sheet? And you know, this is quite a wide question. So before we answer that, I just want to have a quick look at the definition. And from the Oxford English Dictionary, the datasheet is a document providing a specification for a particular product. So in other words, it's our statement to you, our customer, confirming the performance and the limits of our power supply. However, the datasheet is also the first document that you're likely to read from us. So it's a very important document for us to get right. It allows you to form the basis of comparison to other manufacturers. It's also probably the main document that you'll use to base your purchase decision on as well. And obviously we have to keep in mind that it's also the first document that other power supply manufacturers will actually review. So we have to be careful that we don't give too much of our secrets away to the other manufacturers. So it's a bit of a balance in that there. So also, for a complete picture of the power supplies, you also need to read the datasheet in conjunction with the relevant handbook and installation manual and application note. So the answer to the question at the top, you know, for us, it's not really practical to include every possible power supply parameter under all operating conditions. If we did this, then the document would be extremely large and it would take months to compile. And of course, the secondary factor is there's also a balancing act between the needs for you, the customer, whilst also attempting not to give too much information to other manufacturers. So that's the background to the datasheet. So this is a quick overview of the datasheet, and you'll see that there's certain areas that I'll be showing some hints and tips and a bit more background information on those particular parameters. I'm going to concentrate on the electrical parameters and look at the peak power rating curves in particular, and also the lifetime curves. But generally, I'll touch on mechanics, but only very briefly. Okay, so let's crack on and let's start looking at some of these secrets that we're going to reveal. Okay, so on the first page of the datasheet, we have the model selector, and you think it's pretty simple. You know, we list the models available, the output voltages, the adjustment range, but there's some key information in the maximum current under convection and forced air, as well as the maximum power, again under convection cooled or forced air cooling, and also under peak current conditions, under where we have it convection cooled, and you can take more power from the power supply than what we would normally say under certain ambient conditions. So we're going to dive a little bit deeper into those parameters now. So we're going to be looking at max current power, and also related, this is specifically related to thermal measurement. So you'll see this format a few times through the presentation. So first of all, I want to give you a definition of what the maximum current and the maximum power is under convection conditions. And in this case, it is an indication of the maximum amount of current or power that the power supply can deliver continuously without additional cooling. Okay, so no fan cooling, literally it's going to be sitting in the equipment and it will dissipate the heat itself. I won't go through the units, but in this case, for maximum power and maximum current, it's influenced by the input voltage. Of course, if we have a low line voltage, we don't have so much power going into the power supply, and that will affect how much power and current we can actually deliver to your load. The output voltage will affect the amount of current being delivered to your load, and the operating ambient. So particularly if the operating ambient is high, then sometimes we will need to scale back what we deliver to your load because safety critical temperatures may be about to start being exceeded. And also the mounting position of the power supply itself. So you'll see in some of the application notes certain orientations which are preferential for allowing the heat to naturally dissipate from the power supply. WIIS is shorthand for me, is why is it specified? So in some applications, you can't use fan cooling. There's risk of internal contamination being dragged in by the airflow, or maybe there's audible noise limits, say for instance for medical applications, that you can't actually exceed. Therefore, for you need to understand what is the maximum power and current you can deliver without having a fan connected to the system itself. Now, you can see on the right-hand side, we can see the maximum current. The convection current we're saying is about 20 amps, and the maximum power is 250 watts. So bear in mind, this is a 400 watt rated power supply. You can see under convection conditions, we're also derating as well. If you want more details on how we actually evaluate these values, then if you look in our reliability data, then you will see this is an excerpt down at the bottom where you can see the power supply in our chamber. In this case, it's operating at 115 volts and with a 12 volt output. And you can see the output current is 20.83 amps. So that's what we're actually measuring. Okay. Now, the reason why we say indication is that if your application has a different input voltage or a different ambient condition, then you may not be able to achieve the full 20 amps. We need to start looking at the derating curves. Okay, this is going to be very quick. So this is the same parameter, a maximum current and also maximum power, but we're talking about forced air. So now we either have a fan on top of the power supply, or we have an external fan blowing air across it. And again, it's an indication of the maximum power that we can actually deliver, the maximum current we can deliver. Because again, if your application has different conditions that compared to what we have measured at, then you need to refer to the derating curves. So what is the maximum current and the maximum power influenced by? Of course, input voltage, output voltage, as we talked before, as well as the operating ambient. But of course, we now have airspeed as well into our equation. And with the airflow across the power supply, effectively what we're doing is allowing the flow to push localized heating, which will sit inside the power supply, and push that and dissipate it away into the ambient environment. And this means we can actually get more power through the power supply. And we can dissipate that heat. And you can see on the right hand side, our maximum current now has increased from 20 amps up to 33 amps. And also our maximum power has increased from 250 watts up to 400 watts. And again, if you want to see how we do this in practice, how we evaluate, because it's important to compare that to your actual application, then if you look through our reliability data, and again, you'll be able to see how we evaluate the performance there. The key thing for us, and it's absolutely critical for your application, is we really recommend a thermal evaluation. on the power supply, and particularly in the application. So the reason why we recommend this is that we need to make sure that in your application that safety critical parts do not exceed their temperature rating. And you can see this in the handbook. If you look on the right hand side, we have a table of key components on the power supply, and also a map below showing their location, so you know which one to actually to thermocouple. And also you can see the operating limits, and if your power supply, if you're measuring your power supply and those limits are being exceeded, then please contact us, because obviously we would like to give you some support there. Also, the second reason for thermal evaluation is that the ECAP lifetime should not be unknowingly degraded. As I mentioned, the electrolytic is critical for the performance of the power supply, and this because its lifetime is closely related to the ambient temperature that it's actually running at. So the rule of thumb that everyone uses is for every 10 degrees C rise, the electrolytic's life halves. So if you have an electrolytic capacitor sitting in a power supply at 30 degrees C, and it has a 10-year life under those conditions, if the ambient temperature is allowed to increase by 10 degrees C to 40 degrees C, then your 10-year life will be half to 5 years. And from my experience, I've had 15 years experience of electrolytics. This is absolutely a solid rule of thumb here. But the opposite is also true. So if you can actually cool the electrolytic, in other words, cool the power supply even more, then you can actually gain lifetime out of the capacitors. And so if you again have a 30 degrees C operating temperature, and you can reduce that down to 20 degrees C, your lifetime of your power supply will actually double. So it's definitely worthwhile sort of looking at it. And really important is the primary wear out mechanism for power supply is the electrolytic. So we have to make sure we look after that capacitor very well, or those capacitors very well. The final point on this is really on the power supply, how we measure. I've crossed here at the bottom right hand corner. Bench testing is okay just to prove that the power supply works, but it really is bad to understand the thermal performance, because you may have air conditioning, you may have airflow across the power supply itself. So yeah, it's not. We do not recommend bench testing. Really, where the tick is, put it into your application. You'll see the actual real thermal performance of the power supply. Okay. Okay, so I've convinced you now to do your thermal measurements, your thermal trials, and you're monitoring the ECAPs by using K-type thermocouples. So the key thing for us as well is that you also need to give the power supply some time to actually settle down, to stabilize thermally. So this is normally, say, within 2 to 3 hours of initial switch on. Any earlier than that, then you'll record 2 lower temperatures, and this will give you a false estimate of lifetime. So if you allow your power supply to run for approximately 3 hours, then that should be a really good sort of target for stabilizing the thermals. So you'll measure the individual capacitors, and you can see on the map I've highlighted where C15, C14 are, C1, and also C9 and C13. We publish an e-lifetime curve in our application notes, and all you need to do is effectively take your temperatures, and in this case, if I look at C15, this is the red line on the curve, and it's measured at 72 degrees C. And if I draw up to this C15 blue curve and across, then that tells me I'm going to get 6 years life. Now, that's 6 years life of continuous operation. So if you're only using the power supply for 12 hours a day, you double that lifetime. So your actual useful life will be 12 years. Okay. Okay, so that's another important topic is peak current. I'm going to give a power example because there are real opportunities to save cost and also keep your power supply to a small size. So peak current and peak power. So the definition is this is the maximum current or power that can be drawn from the power supply for a limited duration. So it's not continuous, it's actually limited. And it's while it's actually convection cooled. Now, the peak current and power can be repeatedly applied, but it's restricted by the length that you can apply it and also the time that it needs to actually cool down after applying that high power. So it's actually influenced by the input voltage. Of course, we're a low input voltage. We can't deliver the power on the output. Again, the output voltage affects the output current. The operating ambient is clear. And then we got the on time, the peak, how long the peak power is applied, and also the duty cycle, which is the ratio between the peak being applied and the peak not being applied. So why is it specified? So the application demand, current demands can actually fluctuate. So therefore, typically most people who are specifying a power supply will specify the power supply at the peak current. However, there's also quite often that peak current is well above what it would actually run at normal ratings, say continuously. So the result could be oversizing the power supply during the selection. So you can see on the right hand side, previously for convection cooled, we had a 20 amp maximum limit, but under peak current, we can actually now say that you can take that up to 33 amps. Okay, but we don't actually say really what duration you can do that. So I'm going to explain how we look at that. So the customer application is obviously our top secret load. Now, we've been told that the load during startup will consume 350 watts for 5 minutes, and this is once a day. And the nominal load is actually 200 watts continuous. And then the load will change when we acquire an image or record audio, and that will again go up to 350 watts for 5 minutes. And that will be done once every 60 minutes. In this case, the customer really wants convection cooled because it needs to be really quiet because it's secret. However, for the CUS 400M, we state that the maximum power is 250 watts. So traditionally, you'll say, oh, I've got 350 watt demand. I'll put a 350 or 400 watt power supply in that application. So let's see if we can do this with the CUS 400M. So we don't have all the information yet from our customer. So we know what the on time is for the peak load, but we don't know what the input voltage or the ambient operating ambient is or the duty cycle. So I've gone back to top secret negotiations, and they've told me that it's going to be 230 volts and it's going to be sitting at 40 degrees C. And for those who maybe don't really sure what duty cycle is, but effectively it's basically the ratio of on and off time for that peak load. So 100% duty cycle is effectively T on, and T off will be the same duration. Why is it important? Why is it specified? Is a T on for the peak power is a heating element to the power supply itself, and of course the T off is the time for the power supply to actually cool. Excuse me for a minute. I'm just going to take a drink. Excuse me, a bit of a frog in the throat there. So if we look at the actual load profile, it looks a bit complicated, but it's pretty simple. So as we mentioned in the specification, at the T start, we have 350 watts. The worst case is that the application will take an image straight after start. So we have another 5 minutes at 350 watts. And as we said in the spec, after that, it drops down to 200 watts. And then from then on, we can take one image or audio recording an hour. And so this is the first hour, and then we have the second hour with one 350 watt load. So we can calculate the duty cycle quite quickly, because on the worst case condition, we have T on, which is actually 10 minutes. Those are the T start and a T image. And then we've got T off when we go down to normal power. So the duty cycle is actually 20% in this case. And then after this, we have the typical loading where the duty cycle drops down to 9%. Now, from the curves we actually supply in our datasheet, you can see that if we look at 40°C, which is our operating ambient, and we draw the line up to the 230 volt curve, we can see that the maximum on time is actually 30 minutes. So with our 10 minutes of peak power, we're fine with this. But really look at what the big difference is between the input voltage. Between 230 and 115 volts, you can see a huge difference in the T on time capability for the power supply. If we look at the duty cycle, again, we can draw up to 230 volts, and across to the max duty cycle, you can see we can have a maximum duty cycle of 50%. So we've already calculated that we've got a duty cycle of 20%, so we're well within those conditions as well. So we have a good safety margin in this case. We also now need to actually have a look at the output power versus the ambient temperature. And if we look at the output power versus ambient temperature derating curves, you can see we have two. We have convection and conduction cooling, and also we have convection only. So again, if we take our 40°C and we draw up to our 230 volts, you can see we can actually get 350 watts out of the convection and conduction cooled power supply. If we do exactly the same thing for convection only power supply, we can only get about 230 watts out of this power supply. So back to the original question, can we deliver the peak load for convection only? No, we can't. So we would have to advise the customer that they would also have to use convection and conduction cooling to be able to get the 350 watts peak load from that power supply. And just a couple of notes is for conduction cooling, which we also talk about connecting to the chassis. This is not always helpful for the power supply, because say for instance street cabinets where the chassis may be the cabinet itself and it's seeing sunlight during the day, it could actually heat the power supply up. So we have to be a bit careful with this. And because again we're at the thermal limits of the power supply, we would really recommend the thermal trials in the application to really make sure that the safety limits are not exceeded for the power supply itself. Okay, so if we quick look at the at what lifetime we can actually expect, and in this case we can actually start adding up what the average power, and this is what we're interested in. So if we look at all the peak powers and we look at the average powers, so we're going to take in a typical day 65 minutes of 350 watts, and then we've got 655 minutes at 200 watts. If we average that out, then the average power taken from the power supply is just over 200 watts of power. We know under convection cool conditions, the maximum power that we can take is 250 watts continuously. So we're actually running at 85% load on average. So we can now take that 85% load and look at our literally lifetime curve again on the data sheet. We take our 85% load, we draw it up to the 40°C line, which is our green line, and you can see we can draw across and we'll get 5 years of life. But as I mentioned at the beginning, we can't put every different variation on our data sheet. It would be very long. And you can see at the top, this is showing worst case. It's actually at 115 volt input. So what would we actually get out of a 230 volt input? And here we actually provide the data in our reliability document, in our reliability data format, again on the internet. And this time, if we take our 85°C load, or 85% load, sorry, take it up to the 40°C line, and here you can see we can get 11 years life, continuous life out of the power supply. And if it's operated only for 12 hours a day, you'll get 22 years application life. So all looks pretty good. So yes, we can support that secret load, but it has to be conduction and convection cooled, and you can use that CUS 400M pretty well. Okay, we're going to quickly look at some other parameters as well. So these are some options. We've got some mechanics here, and then we've got some fusing and some standby power as well. So in mechanical options, from first sight, it's just really options for mounting or for protection for the power supply, but that's not strictly true. So if we take the various options for CUS 400, we've got this blank, which is our base option. It just allows you to mount on a chassis. You can start chassis cooling with B. We have this thermal plate on the bottom, and then we have the U channel. Again, you're doing conduction cooling. We have the top cover, and then we have the fan cover. But what you'll find is particularly this area, where I'm looking at the improved thermal performance. You get a good thermal performance with B. It's further improved with the U channel, and it's even further improved with the A, with the top cover, and then ultimate cooling is with the fan on top. What kind of difference does it make? Well, I wanted to explain this because it's quite shocking, really. If you look at the open frame for convection and conduction cooling, and also it's taken some of the heat from the chassis, we can get 320 watts. And that's actually the same as well. If you got a U channel with a top cover, you can still get 320 watts from that power supply. But if you look at convection only, in other words, it's not, you're just allowing heat to rise from the power supply. From the open frame, you can get 200 watts. But with a top cover, because we've got a larger surface area that we can drag heat away, we can actually still offer 320 watts. So the actual mechanics really affects the thermal performance. And of course, the thermal performance will also affect your lifetime as well. Let's have a quick look at dual fuse options. So for this range, we offer dual fuse. And the reason why we offer dual fuse is because it always gives protection for the live. So even if by mistake, it's actually connected reverse polarity, there will always be a fuse in the live line. But we also give the option to have a single fuse. And this is primarily for one reason. If you have a dual fuse system, there's a 50-50 chance that if there's an overload within the power supply, either the live fuse or the neutral fuse will blow. If neutral fuse blows, the power supply will switch off, and maybe the electrician who's actually reviewing the power supply, he may not be aware that the live line into the power supply or within the power supply is actually still live. So having a single fuse on the live line always guarantees that the live line is disconnected. But we put dual fuse in primarily for medical requirements. If we quick look at standby power options as well. So again, not many, I get questions about the difference between auxiliary output and also standby output. So this is going to explain this. So this is a basic overview of the power supply. We have our AC input, the input filter, followed by the rectifier and the power factor correction. And you can see we've got two switching circuits here. The top switching circuit is powering the primary output and also an auxiliary output. The second switching circuit is actually powering the standby output. And the key things is particularly with the standby output, it's not affected by any issues with the primary output or the auxiliary output. So if the primary output goes into overload and it starts dropping at voltage, the standby output still remains steady. So it will always be there. If you decide to switch your primary output or your auxiliary output on and off, then that's absolutely fine. But your standby output, again, is unaffected. It will still remain. So this is a good source for possibly, say, for instance, the logic rails for the remote on and off, for the optocouple circuit. And the auxiliary output is typically used for maybe housekeeping or for fan supply. So that, I just want to explain what the difference is between an auxiliary and a standby output, because they are slightly different. A remote sense. Now, remote sense, here we have, I want to give a couple of pointers on good practice. So first of all, what is remote sense? So remote sense is effectively when you deliver power to a load, there's a possibility of dropping a small amount of voltage across your output cables. So by the time it gets to the load, you don't have, say, for instance, full 12-volt output. So by using the remote sense, you can add a couple of additional wires to the load, and then you can actually achieve a closed loop control. So when your power supply senses that maybe it's not 12 volts at the load, it will automatically try to adjust the output voltage up. The output adjustment range is typically limited to 1 volt, and in the case of the CUS400, in fact, it's about half a volt. If I quickly go to the next one, so for good practice, what we'd say is that if you are struggling, if the power supply is struggling to compensate for the load drop, then either reduce your cables to the load, or increase the diameter of the cables to reduce the resistance. Okay, and that will help your remote sense work correctly. You also use shielded and twisted pair cables to avoid noise going back into the power supply. Again, if you've also adjusted your output voltage by the trimmer that we put on the output of the CUS400, then you may already be at the highest output voltage that the power supply can actually deliver. So if the remote sense tries to compensate and push that higher, then it could actually trip the over voltage protection. So you just need to be aware of that if that happens. A key thing as well is to avoid damage to the power supply. Is never sense across a fuse or a switch, because if your sense wires remain connected but your output cables are disconnected, you can actually get back feed into the power supply, higher currents than the sensor resistors can actually cope with, and you'll burn those out. So just be careful of how you connect the remote sense. We're going to have a quick look at some other parameters as well, like leakage current and touch current and power factor. So medical leakage currents, I'm only going to briefly touch on this, but it's a medical power supply, so it's important. If you need another webinar on this, then please let me know, but we're going to quickly flick through the next few slides. So the key thing is leakage currents are important. Definitely for medical applications. You know, we're all controlled electrically internally, and if we apply an external current to our bodies, then that will feel that effect. If we look at the research by Howard M. Hochberg in 1971, you can see at very low current levels it's pretty safe, but you don't really need too much current for it to start becoming a problem for the patient or the user. So we have to be really careful how much current the power supply can actually will leak through its case or through its natural earth leakage. And so we comply to this IEC 60601. In this case, to evaluate that the current that's flowing, we use a 1 kilo ohm resistor, which is actually specified in that application. So, like I said, very quickly, what is medical leakage currents? There are generally 3. So we look at earth leakage currents, a touch current, and also the patient leakage current. Now, we have to look at this under normal conditions and also single fault conditions. Now, depending on those conditions, depends on the current that is allowed to flow from the power supply. So earth leakage, very quickly, as we all know, generally it's effectively a leakage which goes from, say, the live down through the protective earth. So under normal conditions, we can actually, we have to keep the current below 500 microamps, but under fault conditions, then that can be up to 1 milliamp. The touch current, so if you're touching the case or the equipment, then this is has to be below 100 microamps for normal conditions, but if there's a fault, maybe the user has touched another electrical source, then under single fault conditions, the maximum is 500 microamps that we have to supply, or we have to keep it below. The patient leakage current, so this is slightly different. So here the patient is actually connected to the equipment, and this could be through paddles for ultrasound equipment or for blood pressure monitoring, that type of thing. And we have to limit the amount of current that can actually flow through to the patient. So again, we comply generally for BF rating for that. But like I said, too much detail to go in today, but I just wanted to make you aware of that. Okay, so let's have a quick look at power factor correction, because everybody has heard of it. Not a lot of people know really what it's actually for. So power factor correction is really important for the power supply itself, because it's how efficiently the power supply is consuming the mains power. So it's really easy to demonstrate what it is. If we look at the Coke or the beer on the right hand side, the real power that the power supply is actually consuming is the Coke or the beer. But if the voltage and the current isn't actually aligned with each other, then you'll get this reactive power, and this is wasted power. Now, traditionally in electronics, we talk about this linear model where the voltage and current is aligned, and you see this in that first graph there, where the blue voltage and the red current is aligned perfectly. This gives you a power factor of 1. However, with switch mode power supplies, we don't have that linear current. So you can see the voltage increasing, and as the voltage hits a peak, then the power supply would naturally try to pull a lot of current. So we get this burst of current, and this is this middle diagram here. Now, this burst of current has 2 issues. One, it creates a lot of noise, electrical noise, which is a big problem for EMC. But also, we really are losing a lot of power that we need to deliver to your load. So ideally, we need to correct that. So a typical power supply without correction will actually have a power factor of 0.65, and we need to get that closer to 1. If I take a quick example, so the output power for a power supply is the efficiency times by the power factor times by the voltage in and the current in. So it's very simple. So if we take a standard 13 amp current with 230 volt supply, and we say that our power supply is 85% efficient, then using that calculation, we can calculate about 1.6 kilowatts that we can deliver from a power out point of view from the power supply. Now, if we correct the power factor to 0.97, then we'll actually get a 2.46 kilowatt out, almost 2.5 kilowatts. So we actually get a 50% gain in power that we're pulling from the mains, which we can then use to deliver to your load. So it's very important. Okay, installation class. So we only state installation class 1 or class 2 in our power supplies, but it actually has implications. So class 1, as you know, it actually has a ability to have an earth, and class 2, you don't need to connect to earth. It's basically double insulated. Now, this has a key issue for EMC, and it's important when you're comparing particularly class 2 power supplies. So for class 1, we have the advantage where we can take Y caps down to earth and deliver any electrical noise down to earth and dissipate it that way. However, for class 2, we don't have that option. We have to handle that noise internally. So at the very early stages of the design, we're mitigating EMC. And this, if you compare different manufacturers on their EMC performance for class 2, you will really see a wide variation. And we take a lot of time to make sure that we're well below the EMC limits. So when you embed this power supply into your system, then your system will pass your EMC tests very quickly and without little modification. Overcurrent protection, I'll go through this very quickly. So there's lots of different options. We state the power supply has overcurrent protection, but what one? So if we look at the constant current, this is the top graph on here. So here, the output voltage remains steady until we hit a fault current, and then the voltage will fall. So that's one option available to us. We also have the fallback option, where we can have the output voltage remains constant, and then we hit the current limit, and the voltage will fall, but also the current will fall. So the amount of power we're delivering is actually reduced quite significantly, much more than what we saw with the constant current a protection circuit. We look at fold forward. With fold forward, we actually allow the voltage to drop, but also the current to increase slightly. And this is really to help with heavier loads, maybe for restarts. If the fault is cleared, then this gives a better ability to actually restart that load quite quickly. The CUS 400 actually uses Hiccup Mode. And this is quite a simple system where when we detect an overcurrent, then the output will actually switch off. So the voltage will go to 0. And there'll be a set time that will allow the fault to clear. And then the power supply will try to reestablish its output. And then if it's clear, then the output will be reestablished and everything will be working fine. That'd be no problem. We also have the ability for using digital control for other power supplies to actually maybe do that a little bit more intelligently. So maybe on startup, we see a peak current. So we don't start the overcurrent protection at the very beginning, or maybe we only start that after 3 seconds of the power supply operating to give that initial inrush current a chance to dissipate. We can also alter the rest period after a fault current based on the amount of current actually being drawn from the power supply, or based on the amount of overload that's being drawn from the power supply. So again, that's another a key area that we can actually look at. I'm pretty sure that you know a lot about parallel connections. So again, I've been told sometimes, oh, it's just a battery, we can put them in parallel. No, unfortunately not. So if we take this, we have two 400-watt power supplies trying to support an 800-watt load. As we know, the output voltages will be slightly different. So you actually will get back feed into one of the power supplies, or a power supply trying to feed another power supply. So this can't happen. So you'll trip the power supply in this case. So why can't you just put diodes to stop that backfeed? Well, again, the power supplies will be, there's a slight difference in the amount of current it's actually supplying. They won't share equally. And what will typically happen is one power supply will actually be running at 100% load, and the other one will be literally just trickling over. And at some point, it will go into overload. And when it goes into overload, it's a hiccup, so it'll shut its output. So the second power supply will try to support that 800 watt load, and it can't. So it goes into overload, and it will shut its output down, so it will start oscillating. So in this case, no, the diodes will not help. However, if you look at paralleling with a smaller load, so in this case we have a 350 watt load, then this is absolutely fine, because each one of those power supplies can cope with that 350 watt load, and we do need those ORing diodes in there again to protect for backfeed. There's more sophisticated ways of looking at paralleling. So this are higher end hot front end power supply HFE that uses a signal wire that connects between the different power supplies, and this signal wire basically explains to the individual power supplies what load level is actually being supplied, and they can adjust accordingly. There's also droop mode, which you normally find on DIN rail power supplies. You don't need a signal wire, but effectively you can connect multiple DIN rail power supplies together, and the power supply is designed that as it monitors its output current, and the more output current is pulled from it, then the voltage starts to drop. So if you have another power supply in parallel with it, and it's not supplying so much current, then it will actually have a higher voltage than the one that is actually supplying more current. So what will happen is that will supply more current, and its voltage will drop, and it will eventually will balance and actually share the load. Series connections, yes, you can also do this. But a couple of things I should mention: you need to put the diodes again for protection for a power supply itself. And what is also key as well is if you exceed 60 volt limit, then you need to consider the Slv Directive, so the safety extra low voltage, because now your power supply needs protection. So it needs protection from the user and also from accidental short circuit. So you need to cover terminals and that type of thing. So just be aware when you're series in power supplies. This is the last topic I'm just going to go through, and altitude is again key for power supplies. You wouldn't think so, but it is. So the higher we go with altitude, and we say for instance 5,000 meters on our datasheet, as you go up in altitude, then what we find is that the dielectric strength of air starts to reduce. Now we use air within our power supply as an insulator. So it sounds a bit weird, but it basically air separates some components. So as the dielectric strength reduces, we have quite high voltages. We have hundreds of volts inside our power supply. And as the dielectric reduces, then this increases the chances of flashover within the power supply itself. And this can actually mean that you need a lower voltage to create that arc across the power supply. So if we're designing for higher altitudes, then we need to keep those distances actually greater to prevent that sort of situation. So altitude is actually important. And also thermal performance is also degraded at high altitudes. The air is thinner, so it's not we don't have so much convection cooling to drag the air away from the power supply itself. So we can also get overheat at higher temperatures. So there's also a derating that needs to be applied. You can also apply forced air cooling, but again, you probably need higher airspeeds because the air is thinner as well. Okay, so that was really a quick overview of some of the secrets of inside the power supply. I hope some of those are new to you, and probably hopefully not too much repetition. So just on final thoughts, I really hope you found this useful. If you have any questions relating to power supply, then or TDK-Lambda, then please feel free to contact us. If there's anything you want a bit more detail on, or you have other ideas for discussion, then please let me know, and we're more than happy to help there. So only leaves me to know is just open up to questions, Yarav.
Yeah, we have few of them we also already answered. There is a question about the maximum length of the wire, the sense wire. How customer can know what is the maximum length of the sense?
Okay, yeah. So that's also a very good question of how long is a piece of string. So you can have actually quite a long run. So we have some customers who are running sense wires up to 20 meters, and with no problem. There are also some customers who will have sense wires maybe as little as 2 meters, but they will have problems. And the main reason is the resistance of the cable. So what we need to make sure of is that the voltage drop across your load cables are actually, the resistance is actually low. So you can sense, so you don't have such a high voltage drop. And for the sense cables themselves, there's not a lot of current which is not actually flowing through that sense cable itself. So they can be relatively thin. So you should be able to find the specification within our installation manual for those sense cables as well. So yeah, it's possible. You can go up to 20 meters quite easily.
Thanks. Additional question is regarding the U-shape power supply. What is the difference between the U-shape and the PCB only, and what the reason to use it?
Okay, so for the PCB only, so with the PCB, what we're doing is we're basically connecting down to a platform. Now this could be thermally conductive, or it may not be thermally conductive. So we have to assume that it's actually just being convection cooled. However, with a U-shape, so I'll show you here. So with this U-shape here, we actually have a metal base, and we have a thermal path between the power supply down to the base. So we have conduction cooling from the base, but also we can dissipate heat along the base and up the side vanes as well. So we actually get a greater surface area, and we can actually pull more heat from the power supply itself. So even if this isn't actually connected to a conduction cooled surface, the extra surface area of the U channel will allow you to dissipate more heat through convection.
One more questions regarding the parallel connection. Does every power supply can be connected in parallel, and what is the maximum unit that you can use and you can connect in parallel, and if it's in the spec?
Okay, yeah, not every unit can be connected in parallel. We'll clearly state in the datasheet if it can or cannot. If, say for instance, when we talk about parallel, there are two parallel conditions. There's one for stacking power supplies to support a larger load, and this is current sharing. And here, this is what we really mean by paralleling. There's also paralleling but for redundancy, where the actual load is actually lower than the individual power rating of the parallel power supplies. In this case, you can actually put power supplies in parallel, because one of those power supplies can take the full load. The issue is that if you cannot support the full load across multiple power supplies, then you start causing the parallel power supplies going into current limit. So you check the installation manual and the datasheet. It will tell you very clearly how many and if you can. If you have any confusion, then please contact us. We're more than happy to help.
Okay, we have additional question from Evgeny. For general understanding of duty cycle, it on time divided to total period time, not off time. Why do we use different determination when speaking about peak power?
Okay, so in this case, we're assuming that the constant power is running at a level, and when we look at so when we're looking at peak power, we need to understand what the thermal effect on the power supply will be when we deliver or when we take that peak load. So there will be a heating element due to that peak current or the peak power being taken. But also when we remove that peak load and we go back down to a normal load, then we have to have a cooling period to get it back down to that nominal load. And that's what we're looking at, because we need to understand really what the effect of the peak load is actually giving us thermally within inside that power supply. I'm hoping that answers your question. If not, I'm more than happy to have more discussions afterwards.
You answer my question, I hope, also Evgeny. So thank you. Okay, so that is it for questions. Again, Chris, thank you very much.
You're more than welcome.
And to all our customers, if there are any additional subject topics that you want that we will focus in the next webinar, you're welcome to send to your account managers directly to us. And thank you for taking part of our webinar. And again, Chris, thank you very much.
You're more than welcome.
We will close now. Thank you.
Thank you. Cheers.